Bismillahirrahmanirrahim. Assalamu alaikum ji. We were talking about support vector machines. We have covered hard SVM and soft SVM classifiers. Today we will focus on the kernel trick that allows us to handle the classes that are not linearly separable in the feature space. The topic itself is very, very broad, so that we cannot cover it in one lecture or in one video. But the idea here is to give you a quick overview of the topic and how can we use it in SVM. We have shown this to you earlier, that if we have the classes that are not linearly separable, for example, this case, we can project the data to a higher dimensional feature space to make the classes linearly separable. So the data here is 1D. We projected it to 2D such that the classes are linearly separable. We also saw the example for the 2D case. So data in two-dimensional feature space is not linearly separable, but if we project to three-dimensional feature space, we can have hyperplanes separating these two classes, right? Okay, the overview of the kernel trick. When we project the features to a higher dimensional feature space to make the data linearly separable, this is equivalent to increasing the number of features, okay, or increasing the dimensionality of the feature space. The trade-off here is that the optimization problem would be computationally expensive, or solving an optimization problem could be intractable, because the number of, when we increase the number of dimensions, when we increase the number of features, we also increase the number of variables for which we need to solve an optimization problem. So the kernel trick allows us to keep computational tractability. So the kernel trick allows us to have computational efficiency at the same time when we are analyzing the data in the higher dimensional space. First, we need to understand the computations we require to determine SVM classifier. So if you remember, that's how we formulated Lagrange dual optimization problem. So we maximize this Lagrange dual function, which is a concave function. Which is equivalent to minimizing negative of this. So the problem we have is convex optimization, or this is QP. Right? When we solve this QP, we determine these alphas. And once we have these alphas, we can learn the decision boundary using this expression. So this defines the decision boundary. If you see these two formulations, the formulation for decision boundary and formulation of optimization problem, both require the computation of these inner products. So for solving optimization problem, we need to compute the inner product between a pair of data points in your training data. And also, when we need to carry out prediction using this decision boundary, we are required to compute the inner product between the test point and every support vector, right? The computation of inner products depends on the dimensionality of the feature space. If we can find a computationally efficient method to compute the inner products in higher dimensional space, we can compute a linear SVM classifier in higher dimensional space. So this efficient computation of inner products is in fact enabled by the kernel trick. So idea is very simple. We choose mapping to higher dimensional space in a way such that we can compute these inner products in higher dimensional space efficiently, or by employing some of the tricks such that we can compute the inner products in high dimensional space, but we're carrying out these computations efficiently in some lower dimensional space. So that's the whole idea of the kernel trick. Let's develop mathematical formulation to understand this further. So we use phi of x to denote the mapping to the higher dimensional space. It simply means you have points in the low dimensional space, say xi and xj, and you use a mapping function phi to map these points to higher dimensional space. Okay? And phi of xi and phi of xj are the points in the higher dimensional space. And if you want to have a linear classifier in the higher dimensional space, we know that we should have the capability to compute the inner products in the higher dimensional space. Right? So we want to compute the inner products of this type in the higher dimensional space. For certain, not all the mapping functions, we can compute this inner product by carrying out some simple algebraic manipulation in the low dimensional space. And we carry out this manipulation using a kernel function denoted by this capital K. See, the kernel has two inputs, xi and xj. Xi, xj are the points in the lower dimensional space. And this kernel computes the inner product. It returns to the inner product that is in the higher dimensional space. If we choose a mapping to a higher dimensional space for which the kernel trick works, we do not have to pay a computational price for the high dimensionality when we find the best hyperplane. So that is the whole idea of this kernel trick. So this inner product in the higher dimensional space is computationally expensive. And we can carry out this computationally expensive operation in the low dimensional space using this kernel capital K. Right? Okay, let me try to explain this with the help of one example. Very, very simple example. For example, we take D is equal to 2 and we say we have a two-dimensional feature space. We only have two features, x1 and x2. We project this feature space, this lower dimensional feature space, to make it higher dimensional feature space by including quadratic functions. Okay. So we include quadratic features. So previously we had x1, x2. Now we have the square of x1, the square of x2, the cross term x1 times x2, and we also add 1. So this mapping is from two-dimensional space to six-dimensional space, right? We know that if we want to find a separating hyperplane in this six-dimensional space, we are required to compute inner product phi of some point transpose phi of some other point. But in fact, we can compute this by defining a very, very simple kernel. If we define for some point xi and xj, 1 plus xi transpose xj whole square. And that is, you can show that this is in fact equivalent to this. Maybe you stop here and quickly compute this inner product or this formulation, and you can easily show that this is equivalent to this. Okay, what's happening here? That is important. So we're computing inner product. If you compute using this expression, that will be inner product in six-dimensional space. Right? But we're computing the same quantity in a two-dimensional space. Right? So you simply compute this inner product two-dimensional space, you add 1 to it, and you simply square. right? We can say a kernel function enables us to compute inner products in a high dimensional space computationally efficiently using the data points in the low dimensional space, right? Some of the most popular kernel functions which are used for classification or in SVM are, okay, the very naive one would be linear, right? It simply means you're not doing any mapping, right? If this is your kernel, simply inner product, the mapping function is simply x. It's linear. So you're not doing any mapping, right? Polynomial of power m. If I use this kernel, so the mapping function corresponding to this kernel. So we have a kernel. Kernel gives us some quantity that depends on xi and xj. But this quantity is equivalent to the inner product of the 2 points that are obtained. So these 2 points are obtained by mapping xi and xj through some mapping function. So for this kernel, the mapping function is, so we have degree m polynomial of features. So in the previous slide, I showed you the quadratic case. So we had x1, x2, and we have included x1 square, x2 square, x1 times x2, and 1, right? If you have, say, 5 points, x1, x2, x3, x4, x5, 5 features, and I have want to include quadratic features, that would be x1 square plus x2 square, sorry, x1 square, x2 square, x3 square, x4 square, x5 square, and then x1, x2, x2, x3, x3, x4, x1, x4, and so on and so forth. So all m polynomial of the features, right? This mapping function can be interpreted as a mapping from d-dimensional space to d plus m, choose m dimensional space, right? Another very popular function or very widely used function is the Gaussian function. It computes inner product in the low dimensional space, xi and xj in the low dimensional space. And in fact, the mapping function in this case is infinite dimensional. Every point is mapped to a Gaussian. Okay, what is worth noting here, that the intrinsic dimensionality of the data remains d even in the high dimensional space, right? If you connect with this with the curse of dimensionality we studied very earlier in the course, right? So we have a data in the high dimensional space. We said the intrinsic dimensionality is very small so that we can project, we can compact, we can squeeze it into a low dimensional space using some method, for example, PCA. What's happening here, that you have the dimensionality of the data remains d, but we're projecting, we're expanding in a higher dimensional space so that the data becomes linearly separable, right? So the intrinsic dimensionality of the data remains d. So these are the popular, well-known kernel functions, or very widely used kernel functions. Can we have any kernel function? Can we use any function that is a function of x1 and xi and xj as a kernel function? Or how can we define the kernel functions? Okay. So obviously, if we want to check manually whether the kernel function returns the same quantity for the mapping function, this can be complicated, this can be tedious. So there's a well-known theorem, what we call Mercers Theorem, that states we can use every positive semi-definite symmetric function as a kernel. Right? Okay, there are many terms here. Symmetric function, that means if you swap x and xj, you get the same quantity. Right? What do you mean by positive semi-definite? It simply means if you have a symmetric function such that kernel of xi xj is equal to xj xi, we say the kernel function is positive semi-definite if the following gram matrix is positive semi-definite. We know positive semi-definite matrices. We have studied this in detail. So this is PSD matrix is an analog of the multiplication of a quantity by a non-negative quantity. That does not change the plane, right? It remains same. We have talked about PSD matrices in detail. If the gram matrix, if this matrix for a kernel function is positive semi-definite, we say we can use the kernel function. Let's incorporate the kernel in the optimization problem. So assume we are in the high dimensional feature space, and in the high dimensional feature space, we are required to compute these inner products to solve optimization problem, right? So phi of xi is a mapping of xi in the higher dimensional space. Similarly, phi of xj, mapping of xj to the higher dimensional feature space. If now we know how to compute this inner product efficiently using the kernel function. If I incorporate the kernel function k of xi xj, so for this kernel function, the associated mapping function is phi. Right? It could be polynomial, it could be a Gaussian kernel function, right? But here in this alternative formulation, not alternative, in fact, equivalent formulation, we know we can compute this inner product very, very efficiently. For example, if you're using Gaussian kernel function, you simply need to compute xi minus xj Euclidean norm divided by sigma squared or times gamma x, just raise exponent to the negative of that quantity, right? So you can get, but if you want to compute using phi, so we'll computing this in the higher dimensional space, right? This could be computationally expensive, or it could be intractable, in fact, right? So once we solve this problem, we can have a decision boundary, in fact, again, using the kernel. If you recall, when we define decision boundary, we define in the higher dimensional feature space using inner product between support vectors and point in the feature space. But if we use kernel, we can have this formulation of the decision boundary. So I have simply replaced phi transpose xi in phi xj with this kernel. Okay, so it should be xi, my apologies, x. Let me fix this in the notes. And similarly, for any test point z, we say label is 1 f kernel of xi comma z. You sum over support vectors minus theta is greater than 0. So what's happening here? We are living in a lower dimensional space, right? We are solving this optimization problem in the lower dimensional space. We have the formulation of decision boundary in the lower dimensional space. We are carrying out classification in the lower dimensional space. But equivalently, we are manipulating the data in the higher dimensional space. We have a linear boundary in the higher dimensional space, and the consequence of having a linear boundary in the higher dimensional space would be equivalent to a non-linear decision boundary in the lower dimensional space. Are you following this? Sometimes we say that the kernel trick makes your brain hurt when you first learn about it, but it's very, very simple concept. Maybe you can pause the video here, you can review the notes again, and then you come back and see from the very beginning, right? And if you see it once more, you will have a very good understanding of the kernel trick. Right? Maybe I can show you one example using Gaussian function. So we have a binary classification problem. The data is highly non-linear separable. And if I use Gaussian function with this, okay, here we have sigma square and we have gamma. In some textbooks, we use sigma square, and in fact, sigma square is 1 over gamma. Or in some textbooks, we use gamma. So there's only one parameter that defines your kernel function. Either you choose sigma or either you choose gamma. If I learn decision boundary for gamma is equal to 100, I get this non-linear boundary using SVM. So, okay, how do you interpret this? So we are mapping this two-dimensional data to infinite dimensional feature space. And there we are learning a hyperplane separating the two classes. And when we project all of this back into dimensional space, we get this. The hyperplane corresponds to this non-linear decision boundary. Right? Okay, so we stop here with the kernel trick. So we know how do we handle the classes that are not linearly separable using SVM by employing the kernel function. Right? We stop here and we'll continue in the next video, inshallah. Allah Hafiz.